Alrighty. Howdy, folks. So let's look at chapter 2 in the textbook. It's all about limits. Okay. Should I start with this PowerPoint? Nah, maybe I'll go to the GeoGebra. Okay, let me tell you something. The concept of limits is incredibly important. The whole of calculus depends on this very concept of limits, right? It's not so difficult to understand it, but that doesn't mean it's not important, okay? So let me give you a motivation as to what's the big deal about this stupid limits, okay? Let me try. Suppose I have a pizza, Super Bowl time, and I ordered me a large pizza, and the fat guy that I am, I'm capable of eating a large pizza all by myself. And so it so happens that before the game starts, I ate half the pizza. Cool. And then in the halftime, I ate 1/2 of what was left over. Cool. So how much did I eat in the halftime? 1/2 of 1/2, which is 1/4, right? And then after the game was finished, I ate 1/2 of what was left over. So that means this time I ate 1/8, right? Now I hope you get the picture. After that, I ate half of what was left over, which is 1/16, 1/32, 1/64, and so on. Right? But now notice, I can keep on eating half of what is left over infinitely. Would you agree? I mean, theoretically, I can keep on eating infinitely this pizza. Of course, what you notice is, as I keep going further and further into the pizza, what I'm left with is a very, very tiny sliver. The pizza that I get to eat is getting smaller and smaller and smaller, right? So, the truth is, we ask ourselves, wait a minute, even though theoretically we can keep on doing this pizza eating infinitely, by the time I get done, how much pizza would I have eaten? Could I have eaten, because I ate infinite number of times, I would have eaten infinite number of pizzas? No, it's just one pizza. I'm getting to eat smaller and smaller portions of it each time. Things like this were the motivation for limits. So the way we say this is, limit as n approaches infinity, the amount of pizza I get to eat is 1. Right? Even though n is what? N is the number of times I get to eat. The first time I got to eat half of it, the second time I got to eat 1/4 of what was left over, and so on. So if I eat infinite number of times, still that adds up to only 1 pizza. And this is somewhat related to the Xenos Paradox. If Hercules, who is considered to be really fast, and a tortoise, which is considered to be pretty slow, if the tortoise were to be given 100 meters with a head start, and they are running a race, would Hercules ever catch up with the tortoise? And the argument is, well, it takes a certain amount of time for Hercules to cover 1/2 of the distance, and to cover the remaining 1/2, it takes half of remaining. It would take some amount of time, and you can keep on doing it. So theoretically, Hercules will never catch up with the tortoise, was the idea. But then once the concept of limits came up, then you could explain all of this. So infinite doesn't necessarily mean it has to be, the final outcome has to be infinity. Okay, so that's a simple beginning for this, and let me get into slightly more involved part of this one. So let's look at this. What do I have here? I have a graph of some curve y equals some f of x. Exactly what is it? Yeah, let's not worry about that. Okay, and so the question is, if I said, hey, can you find f of a for me from this graph? If I asked you, you will say, piece of cake, man. I'm going to go to an x value of a. So there is a point whose x value is a, that is on the x-axis. I'll go there, and then I'll draw a vertical line there. And wherever the vertical line cuts the graph of y equals f of x, I will look at that point, and then at that point, this time I will draw a horizontal line, right? And whatever is the y value there, that is my f of a, right? Let's say that value happens to be some L. Would you agree this is what you would do? If I asked you for f of a, go to x value of a, draw a vertical line, see where it cuts the graph, draw a horizontal line at the intersection point, and the y value there is f of a, or in this case, like I said, L. Piece of cake. But then I'll ask you to do something weird this time. Yep, I know this is how you can find f of a, but tell me this. What if you were to start at some x value to the right of a? Okay, you see this vertical line? My point is to draw this vertical line to the right of a. And then I'll ask you, hey, what's the y value at this x? And simply, you'll draw a vertical line and see where it cuts the graph. And then you will draw a horizontal line at the intersection point. And whatever that y value is, you will say that is your f of x. Would you agree? You were at some x value to the right of a, and you found the corresponding y value. Now I'll say, okay, do one thing for me, please. Get closer and closer each time. Now that you have, where's my B? Okay. Now get closer and closer to A. And each time you try to figure out the y value, right? Would you agree? This x was far away. Now x is a little closer to A. And the y value is something. And now I got even closer. And each time I'm getting closer and closer. Let me phrase it correctly. Each time I'm letting x get closer and closer to A from the right hand side. Now I want to ask you, hey, when you do that, what are the y values getting closer and closer to? And you will probably go, duh, whatever is f of a, these f of x values are getting closer and closer to that f of a. And guess what? You are right. Now you probably are like, man, what's the big deal about this? Well, the big deal is, this is when we say, as x approaches A, f of x approaches L. Or limit of f of x as x approaches A is equal to L. That's the concept of a limit. What is that? We are letting x merely approach A. X is not going to be ever equal to A. We don't care about what happens when x equals A, right? when x merely approaches a, what do the y values approach? That is the concept of limit. Cool. But then there is a small issue here. We are letting, I need to move left. Okay. We are, come on, Sammy. Earlier, we let x go from we let x approach a from the right hand side. Well, would the same thing happen if we let x approach a from the left hand side to the left of a? So that's what I'm planning to show you here. Slightly to the left of a, and I'm getting closer, 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 right? As I do this, what are the y values getting closer and closer to? Once again, to that same L value. In this case, we say limit of f of x as x approaches a is equal to L. Cool? Now, like I said, if you are going, oh, come on, this is a stupid, simple idea. What's the big deal about this? I agree. It's not such a big deal. But then, let me ask you one thing. What if the situation is something like this? Or what is the situation? I don't know if you can see this or not. So let me remove the horizontal line X. Okay. And also, yeah. Do you notice this hole in the graph? That's a hole in the graph, folks. Okay. Now, in this case, where there is a hole in the graph, if I were to ask you what is f of a, you would have to say f of a is undefined, because at x equal to a, when x equals a, the corresponding y value is unknown. There is a hole at x equal to a, right? Now, in a case like this, even though f of a is not defined, we can still talk about this limit concept. If you recall, what I said is, as x approaches a without equaling a. The moment x equals a, at least in this case, function is undefined. Yeah, we don't care about that. We are more interested in as x approaches a, what happens. And we can confidently say, well, at least in this case, as x approaches a, whether from the right hand side or from the left hand side, f of x approaches L. So, limit of f of x as x approaches a equals L. Cool? Boy, that is the point, ladies and gentlemen, I'm trying to drive at. All right. Cool. Let's do with that. Let's go to my PowerPoint presentation and start with some definitions and things like that. Cool. Let f be a function defined everywhere in the neighborhood of a except perhaps at a itself. What? This is an important condition. When you want to talk about limit of some function f, rather limit of f of x as x approaches a, that function f must be defined everywhere in the neighborhood of a. Okay, which means there must be an open interval containing a where this function is definitely defined. If that is not even, if the function is not defined in the neighborhood of a, we cannot talk about the limit of f of x as x approaches a. So that is the minimum requirement, the one of the requirements at least. Okay, and then we say limit of f of x as x approaches a equals L if something happens. If we can make f of x arbitrarily close to L. What do you mean by arbitrarily close? That means as close as you want to L. The f of x values can be made to be as close to L as possible. How do you do that? By taking x sufficiently close to A but not equal to A. Okay, so as you notice that I was able to move that vertical line starting far away from A and then getting it closer and closer and closer to A. And when I did that, the y values were getting closer and closer to L, right? I can get it as close to L as possible, as close as you want. You are the one who's demanding. So I can accede to your request and I can make f of x as close to L as you want. And for that, I may need to get pretty darn close to A. But the only thing is, I cannot let x equal A. All right? So that's the idea. If you understood this concept, folks, that's fine. If you didn't understand, don't sweat too much. There is something called precise definition of limit, and we can talk about it later. But just to give some idea. What's this figure? Look at this one. If I said, hey, boys and girls, there is this graph of y equals f of x that looks like this. Now, could you tell me what f of 0 is? And you will go, wait a minute, let me go to x equal to 0, and you come here. Uh-oh. F of 0 is not even defined. Right? There is a vertical asymptote, if you remember from pre-calculus. There's a vertical asymptote at x equal to 0. So here it so happens that f of 0 is undefined. Here is the beauty of limits. Even though f of 0 itself is undefined, could you now ask yourself in terms of limits? As x approaches 0, say from the right, what are the y values approaching? Would you agree that the y values are getting bigger and bigger and bigger? That means these y or f of x values are approaching infinity? Yep. And similarly, when x approaches 0 from the left, aren't f of x values approaching positive infinity? So, as x approaches 0 either from right or from the left, f of x values are approaching infinity. Can you make a limit statement based on that? Did you say limit of f of x as x approaches 0 is infinity? If you did, pat yourself on the back. You did an awesome job. That's exactly the idea. In this case, limit of f of x as x approaches 0 is infinity, because as x approaches 0 either from the right or from the left, f of x values approach infinity. Cool? There's one more scenario. Take a look at this scenario. So I got this curve, y equals f of x. In this case, if, how should I put it? Okay, let me put it this way. Can I ask you, hey, boys and girls, can you find f of 0 for me? You'll say, piece of cake, man, I'm going to go to x equal to 0. Looks like f of 0 is 0. Yes, you're right. Find f of 1 for me, wherever it is, some x equals 1, you go, some value here, man. I'll take that, okay? And so, you can find f of 0, f of 1, f of 2, so on. But would it make any sense if I said, what is f of infinity? There is no such thing. You should, I mean, a mathematician would cringe if you say, all right, what is f of infinity? No, infinity is not a number like that you could say, like f of 1, you could say f of infinity. That concept doesn't make sense. However, even though we said f of infinity doesn't make sense, we kind of think, yeah, man, like what I'm asking is, when x is a very large number, what is f of that very large number? Right? That seems to make sense. But that concept is not precise. However, when you use the concept of a limit, it all makes perfect sense. In what way here? We can say, can you tell me what is limit of f of x as x approaches infinity? Right? As x approaches infinity, what are the f of x values approaching? Could you answer that question? You most certainly can. Right? If I had a vertical line, if I could go to that GeoGebra thing that I did, I would be doing a vertical line and moving that vertical line to the right and keep on moving it to the right. And each time I'd look at the y values. And as you can see, as x gets bigger and bigger, approaching infinity, the y values would be approaching this L. Can you express that as a limit? Can you give it a try? Limit of f of x as x approaches infinity equals L. See? So we looked at limit of f of x as x approaches a equals L. Limit of f of x as x approaches 0 is infinity, and also the concept of limit of f of x as x approaches infinity equals L. Cool? All right. So let's dig into it a little more. Left hand limit and right hand limit. I already talked about this, but let's get to something interesting. Take a look at this graph of y equals f of x. Now, think about it just a little. If I let x approach a from the right hand side, if I let x approach a from the right, what are the f of x values approaching? That means, hang on, man, I'm going to go and pick a point to the right of a and draw a vertical line there and see what the f of x value is. It's 2 here. If I get a little closer, still 2, 2, 2, 2, 2. Oh, as x approaches a from the right, the value is 2. Yep, you're right. However, notice this time, if we let x approach a from the left, well, that means I start somewhere here. The y value is 1. I get a little closer, still 1. 1, 1, 1, 1. So as x approaches a from the left, the y values are approaching 1. So we have to say this as limit as x approaches a plus, which means a from the right, of f of x is equal to 2, right? And limit of f of x as x approaches a minus, that is, x approaches a from the left, f of x, that limit is equal to positive 1. Cool? So this a plus thing is called the right hand limit, and a minus thing is the left hand limit, because we are letting x approach a from the left hand side, so we call it left hand limit. Okay, now comes an interesting question. What is limit of f of x as x approaches a? Right? It's both 1 and 2, man. No, that's a no. You cannot tell me 1 and 2 and so on. And in fact, mathematicians have decided, mathematicians in the sense, good old Leibniz and Newton, they are the ones who invented calculus. They said, well, in a situation like this, you just say the limit of f of x as x approaches, say, d and e. What? Does not exist. Because the left-hand limit and right-hand limit are not equal, we'll just say limit does not exist. Cool? All right. And now, based on this, we can say something like this. Limit of f of x as x approaches a equals L, if and only if limit of f of x as x approaches a minus equals L, and limit of f of x as x approaches a plus is equal to L. Now do you see? I covered what chapter in the very first lecture? Logic. Did we bump into something called biconditional if and only if? Do you recall exactly what if and only if meant? P if and only if Q. P if and only if Q means if P then Q is true, and also the converse if Q then P is true. How do you apply that to this one? This means if limit of f of x as x approaches a equals L, then the left-hand limit and right-hand limit are automatically equal to L. Okay, if this part is true, then that part is guaranteed to be true. So if somebody tells you, hey, I found that limit of f of x as x approaches 2 is equal to 10. Immediately you can say, or you mean limit of f of x as x approached 2 from the left is equal to 10, and limit of f of x as x approached 2 from the right is also equal to 10. And you would be right. On the other hand, the same thing could be phrased in a different way, right? The other part is true. That is, the right-hand side is true. The left limit is L, right limit is also L. What's the limit then? Oh, right, because they are equal, the two left and right limits are equal, the limit itself must be equal to L, right? So that is the idea of this left hand and right hand limit. And like I said, we will be using that logic stuff quite a bit throughout the course. Okay, all right. What's the next concept? We saw that in this case, where the left limit was not equal to the right limit, limit did not exist, right? Are there any other situations where the limit wouldn't exist? Now take a look at this graph of y equals sine of pi over x. This is how it looks. Now, if I asked you, hey boys and girls, this is y f of x equals sine of pi over x. What is limit of f of x as x approaches 0 from the right? X approaches 0 from the right. Wait a minute. If you were to take an x value to the right of 0, right, that's what you're supposed to do. X approaches 0 from the right means pick some x value to the right of 0. What's the y value? Say this is the y value. Now, if you got a little closer, then the y value is different. If you got even a little closer, let's say the 0 is the y value, and you got a little closer, some negative value. And then it goes up back to +1 and all kinds of values in between, and this one keeps oscillating. Like there is no particular value that this is approaching. It's oscillating back and forth between -1 and +1. Right? The y values are oscillating between -1 and +1 as x is approaching 0 from the right. And here again, because the f of x values are not approaching any particular number, we have to say the limit does not exist. So limit of sine of pi over x as x approaches 0 plus does not exist. Cool. All right. And limit as sine of pi over x as x approaches 0 itself, of course, does not exist. Excuse me. The assumption is, in fact, I showed you only the right half of it. The left half also would be a mirror image of what you're seeing here. And so we can conclude the limit does not exist. All right. And vertical asymptotes. Yeah. Based on what you learned in pre-calculus, would you call the x equals 2 that as a vertical asymptote of this graph? Yep, that is a vertical asymptote. Cool. Can we now become more precise? Why do we call this as a vertical, x equals 2 as a vertical asymptote? Well, you know, the thing is approaching infinity. There was no clarity in pre-calculus about why that should be called as a vertical asymptote. You may have had some intuitive understanding, and the teacher could give you some intuitive understanding, but there is no mathematical precision to this. However, now that you know limits, let me ask you this. What is limit of f of x as x approaches 2 minus, that is, approaches 2 from the left? Clear. If x from the left, that's the y value. Get closer, the y value is increasing. Oh, positive infinity. Interesting. Limit as x approaches 2 minus of f of x is equal to infinity, and x equals 2 is a vertical asymptote. Okay, let's keep that in mind. Let's go to this scenario. What is limit of f of x as x approaches 2 from the right? Oh, that's also equal to infinity. So is this a vertical asymptote? Yep. Do I have other scenarios? Continue. Ooh. Now, is x equals to a vertical asymptote? Yes. Can you guess as to what limit of f of x as x approaches 2 minus is? That is, we let x approach 2 from the left. What are the y values approaching? Oh, they're getting more and more negative, approaching negative infinity. So in this case, limit of f of x as x approaches 2 minus is negative infinity, and similarly, in this case, limit of f of x as x approaches 2 plus is negative infinity. Do you agree? And so, once you understand this concept, we can define this vertical asymptote much more precisely. The vertical line x equals a is called the vertical asymptote of the curve y equals f of x if at least one of the following statements is true. Either limit of f of x as x approaches a equals infinity, right, which means both the left hand and right hand limits are also infinity, or limit of f of x as x approaches a is negative infinity, we would still say x equals a is the vertical asymptote. Or if the right hand limit is infinity, or right hand limit is negative infinity, and these are the conditions. Left hand limit is positive infinity, or left hand limit is negative. If any one of these statements is true, we say x equals a is the vertical asymptote. Cool? That's all I wanted to show you. With that, now in the book there are problems like this. They show you a graph like this and they say, all right, boys and girls, tell me what certain limits are. Okay, let me ask you those questions. 1. What's limit of f of x as x approaches -3 is? Can you answer that? X approaches -3. From the right, infinity. From the left, also positive infinity. Oh, since the left hand and right hand limits are both the same, equal to positive infinity, we'll say positive infinity. Right? As simple as that. And what about limit of f of x as x approaches -1? -1. Oh, x, this is -1. X equals -1. From the left hand side, negative infinity. From the right, also negative infinity. Right? Would you agree this is negative infinity? That's it. Cool. What is f of 1? Be careful. What is that? I'm asking, what is f of 1? Is f of 1 0? Nope. There's a hollow circle there, a hole there. So f of 1 is not 0. In fact, there is a solid dot over there showing that f of 1 is actually equal to 2. Cool. F of 1 is actually equal to 2, folks. Now comes the interesting question. What is limit of f of x as x approaches 1 minus? As x is approaching 1 from the left, what are the y values approaching? Would you say 0? Yeah. Now notice, we are not making, please pay attention to this. When we say let x approach 1 from the left, we mean literally approach, but never let x equal 1. The moment we make x equal 1, of course, we are jumping to 2. We don't want that. So our question and our focus is on what happens if we merely let x approach 1 from the left. Oh, clearly, in that case, y values are approaching 0. So this limit is 0. What about limit of f of x as x approaches 1 plus from the right? Same idea. The y values are getting closer and closer to 0. So as a limit, we should say that's equal to 0. What is limit of f of x as x approaches 1 then? Oh, the left hand limit is 0 and the right hand limit is also 0. So this has to be 0. Right? Now let's look at results 3 through 6 and get something, especially 3 and 6. Focus on them. Notice how even though f of 1 itself is equal to 2, the actual function's value at x equal to 1 is 2. Limit as x approaches 1 is actually 0. Right? That is entirely possible, and that's what makes limit fascinating. Cool? A few more questions. What about limit as x approaches 2 minus? X approaches 2, positive 2. Don't say, hey, -2 is over there, man. I'm not talking about -2. I'm talking about 2 minus. That means 2, x approaching 2 from the left. In that case, as we see, as x approaches 2 from the left, the y values are going more and more negative. So that's negative infinity. However, as x approaches 2 from the right, the y values are getting...
Sorry, I don't know that.
Y values are approaching positive infinity. Man. And so, that my Amazon thing going crazy. I cannot even say the name. Just threw me off. Sorry about that. All right. So can you anticipate the question? And the question is, what is limit of f of x as x approaches 2 then? And your answer should be? Did you say does not exist? If you did, again, pat yourself on the back. You're absolutely right. Cool. Why is that? Because the left hand limit is not equal to right hand limit. As simple as that. Okay. 10. Ooh. Are there any vertical asymptotes in this case? Is there a vertical asymptote at x equals -3? Yup. Why can on what grounds can we claim that x equals -3 there is a vertical asymptote? Because limit of f of x as x approaches -3 is equal to infinity. That's what we looked at in the definition. Cool. Is there a vertical asymptote at x equals -1? Yep. Why is that? Because limit of f of x as x approaches -1 is negative infinity. Even in that situation, we have to say x equals -1 is a vertical asymptote. Is x equals 2 a vertical asymptote? Yep, because the left-hand limit is negative infinity. That itself would have been sufficient. In addition to that, the right-hand limit is positive infinity. So, ladies and gentlemen, we got 3 vertical asymptotes. Ooh, I lied. X equals 5. Sammy. We didn't compute that limit, and that's why I got. Okay, so x equals 5 is also a vertical asymptote. Sorry about that. Cool. Are we clear, folks? Alrighty, moving along. Ooh. Determine the infinite limit. This is if you feel like pausing at this time, that may not be a bad idea, but I think I'll just keep going. So take a look at this one. Up until now, what we did is we said we had graphs, and based on the graphs, we determined what the limit is. But let's graduate to something different. Let's ask, what do you think the limit as x approaches 5 plus of x plus 1 over x minus 5 should be? Are we in a position to answering a question like this? Well, one way is to draw the graph of this and from that be able to determine. Or another way is if we had a graph of the function, isn't going to be rather easy, right? Since we don't, we could do this. As a first step, plug x equals 5 and see what happens. When you do, the top is 6 over 5 minus 5. 6 over 0. What is 6 over 0? Do not tell me that's equal to 0. Division by 0 does not exist. Undefined. 6 over 0 is undefined. Right? Okay. But as a limit, can we talk about what this is? And so what we do is, in the second step, recognize we are asked for a limit of x, limit as x approaches 5 from the right. So plug a value for x that is slightly to the right of 5. What am I asking you to do? Plug a value for x that is slightly to the right of 5. Can you think of a number that is slightly greater than 5? 5.1? Right? Ooh, I took 5.01. Okay. Now, plug 5.01, which happens to be to the right of 5. When you do, you get 6.01 on the top over 5.01 minus 5, which is positive 0.1. right? And so you get 6.01 divided by 0.001, which is 601. Okay. Now plug x equals 5.001, which is even closer to 5 than before. And when you do that, you get 6.001 over 0.001, which is 6001, right? When we were slightly farther away at 5.01, we got 601, and when we got closer, we got 6001, right? Well, we could continue to do that, but I think that is enough to see that recognize that here as x is getting closer and closer to 5, f of x is getting to be a larger and larger positive number. So we can conclude that as a limit, the answer must be infinity. This is a decent way. So what are the steps? Just plug first. Do you get a scenario of 0 in the denominator with a non-zero number on the top? Pay attention to what I just said. 0 in the bottom, but a non-zero number on the top. Then in that case, we can talk about something being either positive infinity or negative infinity. We need to figure that out. So to do that, now pick a number slightly to the right of 5, like a 5.01, and see what its value is. Now get even closer and see what the value is. Based on that, if you needed one more point, go ahead at 5.0001, 3 zeros 1, okay? If you wanted to do that to get an idea, that's fine. But notice that trend shows you that the numbers, the quotient is getting bigger and bigger. So we can simply conclude getting bigger and bigger as a positive number. So we can say the limit is infinity, positive infinity. Okay. All right. Let's pick another one. Determine the infinite limit. Ooh. Square root of x over the quantity x minus 3 squared. Okay. Limit as x approaches 3 from the left. What was our first step? Just plug 3 straight away. Okay. You get square root of 3 on the top, a non-zero number. In the bottom, you get 3 minus 3 is 0, 0 square is 0. A non-zero number divided by 0. This is some kind of an infinity involved here. So let's figure out, is it positive infinity or negative infinity? Okay. So what should we pick? We should plug a value that is slightly to the left of 3, right? Can you tell me a number that is slightly to the left of 3? Not negative 3, okay? Slightly to the left of positive 3 is what I'm asking. 2.99, right? Okay, cool. So let's try to get a sense of what happens when x takes on a value of 2.99. And we get 2.9 square root of 2.99, we don't care how much that is, divided by 2.99 minus 3 is negative 0.01, but when you square a 0.01, you get 0.301, right? Square root of 3 is something like 1.732. Divide that by this small number. I don't care exactly what it is, but that's going to be a pretty large number, right? Because we are dividing by 0.00001. Or if you multiply both the top and the bottom by 10,000, right? So you get something 1.7 times 10,000. So roughly around 17,000 is what you get. 10,000 times 1.7, 17,000. Yep. So close to something like a 17,000 is what you get. And so if we let x get closer, that's going to be even a larger number, because we would be dividing by a much smaller number. Okay, so once again we can conclude the limit must be positive infinity. Are you getting the hang of this, folks? Okay, and that's what I wanted to show you, and you are ready to solve some homework problems in exercise 2.